Here's the system that we observed floating in the water. When we add a weight to this end, that pushes the end down. The other end comes up. This thing rotates about an axis through its center here. An axis comes right along here. A little hard to do that with the camera, but the axis is right here. So it rotates as if it was rotating on some object. When it rotates, its angular position changes. We observed the angular position change when we added a washer to this side. Okay, the angular position changed. When we released that weight, the angular position changed back to where it was. That weight exerted a torque about this axis of rotation. So we have a situation where when we displace this thing, if I just push it down and let it bob back up, it's going to bob back up, and then it's going to rotate back and forth like this. It's going to just kind of oscillate back and forth in a simple harmonic motion, where we measure the motion as the angular displacement in response to a restoring torque rather than a restoring force. We begin analyzing the situation as follows. This is a side view of what we just saw. If we add 15 grams here, we observed a delta X of about 0.5 centimeters. That is, this thing sunk 0.5 centimeters deeper into the water. Now the system, the styrofoam had a length of about 10 centimeters, and it was about 4 centimeters from the center out to the center of the washer. From this information, from the delta X and the dimensions of this styrofoam piece, we can calculate the angular displacement of the system. From the 15 grams, weight acting on the 15 grams at a distance of 4 centimeters from the axis of rotation, we can calculate the torque. This is going to be just like a situation where we have a force and a displacement, except now we have, instead of force, torque. Instead of displacement, angular displacement. It's just like what we did with the 3 kilogram masses when we added weight and measured the displacement to get K. Except again, torque instead of force, angular displacement instead of displacement. Okay, the torque that we got here was the weight of the 15 kilogram, the 15 gram mass, which is the 0.015 kilograms times 9.8 meters per second squared, and multiplied by the moment arm, which was the 0.04 meters, the 4 centimeters from the axis of rotation out to the point of application. This thing was floating pretty near horizontal, so that the force is pretty much always perpendicular to the moment arm here. It's not exactly so, but it's close enough that we don't really have to worry much about the difference. In any case, we find that the restoring torque here was 0.006 meter newtons. And we'll note that the restoring torque is negative in this case. We push down, the restoring torque is back this way, which is a clockwise rotation, which is what we conventionally call a negative rotation. Now, our delta theta, remember that we had a displacement of 0.5 centimeters at a 5 centimeter distance from the center of rotation. So our delta theta is going to be this little angle in here, this little sliver of an angle, which is going to be the inverse tangent of the opposite side over the adjacent, or of 0.5 centimeters over 5 centimeters, and we divide that out, we get about 0.1 radian. Now, if we have torque equal negative k theta, which is analogous to force equals negative k times x. K is just our restoring torque constant now instead of restoring force constant. We're using theta instead of x. We're using torque instead of force. In any case, it's going to follow that whatever torque we induce, any delta tau, is going to equal negative k times our delta theta. And we've got a delta tau here and a delta theta here, so we're going to be easily able to calculate k. It's negative delta tau over delta theta, and the delta tau was negative 0.006 meter newtons over 0.1 radian, we get 0.06 meter Newton per radian. That's our restoring torque constant. Now how do we calculate omega? For regular simple harmonic motion, it's the square root of k over m. What takes the place of m in rotational motion? Moment of inertia, I. So omega is going to be the square root of k over I, and I is going to be the sum of the mr squareds for the system. If we look at the system again, we see that it consists of a pretty small mass of styrofoam plus 2, 4, 6, 8 washers. And those 8 washers are all at the same distance from the axis of rotation, 0.04 meters. We're going to ignore the styrofoam. It turns out it doesn't contribute very much at all to the moment of inertia of this system. Doesn't have much mass. Its total mass is less than the mass of one washer, and a lot of the mass is concentrated nearer the center than the washers were. So we're going to find that the total mass of the washers, which is 0.12 kilograms, times their common distance from the center, 0.04 meters, that quantity squared gives us a moment of inertia of 0.00192 kilogram meters squared, giving us an omega of 17.6 radians per second. And that 17.6 radians per second predicts a period of 0.36 cycles per second, and that's not right, it's 0.36 seconds per cycle. We observe about 0.4 seconds per cycle. Okay, we have to change these cycles per second here, they're backwards. If we account for the moment of inertia of the styrofoam by taking the approximate 5-gram mass of the styrofoam times the 10 centimeter, with the 10 centimeter length using 1/12 ml squared, since we're rotating about the center, we get this, which is insignificant compared to the moment of inertia of the system, so we think that this is a pretty good comparison.